Welcome to EconTalk, part of the Library of Economics and Liberty. I'm your host, Russ Roberts of Stanford University's Hoover Institution. Our website is econtalk.org, where you can subscribe, comment on this podcast, and find links and other information related to today's conversation. You'll also find our archives, where you can listen to every episode we've ever done going back to 2006. Our email address is mail@econtalk.org. We'd love to hear from you. Today is August 26, 2019, and my guest is physicist and author Sabine Hossenfelder, a research fellow at the Frankfurt Institute for Advanced Studies. She has written more than 70 research articles, mostly dedicated to quantum gravity and physics beyond the standard model. And she is the author of the book, Lost in Math, How Beauty Leads Physics Astray. Sabine, welcome to EconTalk.
Hello. I
want listeners to know that this book is in many ways a tour of the state of our knowledge about the physical world. But it's a lot more than that. Along the way, you raise many philosophical and methodological questions that I think are deeply related to problems in economics and science generally and social science. So while at times we're going to be talking about physics, and we're also going to be talking about epistemology. That is, how do we know what we know, and the challenges of fads in science, the challenge of biases, which is a big theme of this program. And these are not just problems in physics or economics, obviously, but are the challenges of being a human being. Now, much of your book is an attack on the idea that a theory in physics needs to be beautiful. What's wrong with the idea of beauty? Aren't the best theories in physics indeed beautiful?
I would say yes, they are. There is nothing wrong a priori with finding beauty in theories that describe nature. The problem begins if scientists use specific notions of beauty to develop new theories, and then they are unwilling to give up these ideals of beauty if the theories do not work.
And in particular, you make some bold and I would say damning condemnations of some of the most exciting and really current theories in physics. I would list among them supersymmetry, the idea that there's a multiverse, that there are multiple universes coexisting at the same time, string theory. You argue that these have little or either have no empirical implications, or the empirical implications have failed to be seen. Is that a good summary of how you look at what are the most dramatic aspects of physics, really, of the last 50 years?
Yes, basically, I think that's what has happened. So you named string theory, supersymmetry. One could maybe add to this list this idea of a grand unified force of the interaction.
Yep.
It's also a pretty idea. And those were really good ideas in the 1970s, 1980s. And it was definitely something that people should have tried, and they tried it and it didn't work. And then what happened was that they didn't just stop pursuing this line of research, but instead they made these theories even more complicated and arcane, until basically they became entirely untestable. And the multiverse that you just named is basically one step further, which is untestable from the original idea.
From the get-go, yeah. Although there's a Spider-Man movie, I don't know if you've seen it. It's called, I think it's called Spider-Man in the Multiverse, something like that, or it's got a slightly better title than that, maybe. Have you seen that movie?
No, I watched one of the Spider-Mans, but not this one.
You've seen then a tiny fraction of the Spider-Man movies. There are so many of them, but it's actually quite imaginative. It may even be accurate in terms of its, there's portals and ways to move between the multiverses. It's quite aesthetically pleasing, that movie. I found it extremely beautiful, actually. It's an animation. And it allows, the idea of the multiverse allows there to be different versions of Spider-Man with different characteristics sort of coexisting, and they all get thrown together. But that's someone's imagination. And as you point out, it's not empirically testable. It reminds me of this claim, which I hope we can talk about a little bit, that we're living in a computer simulation. I guess we won't know for sure until the simulator sends us an email that lets us know. But other than that, it's kind of hard to understand how you would know such a thing.
Yeah, so, don't get me wrong. I very much like this idea of the multiverse. I find it very thought stimulating. And as you just said, it makes for great science fiction, or maybe you want to call it fantasy. My problems begin if people start to insist that it is science. So this idea with us living in a computer simulation, that's basically a form of the multiverse.
Yeah, and it's... I'm not going to name the person. I don't know the name of the person. I was just so appalled at the statement that I just stopped reading. But a person at, I think, MIT, which is a fine university, and it was someone in a prestigious department at MIT, declared that there's at least a 50% chance that we're living in I can't say it without laughing, in a computer simulation. Because for a person who purports to be a scientist, to put a probability on something like that strikes me as you say, unscientific.
Yeah, I think I know who you're talking about.
I mean, I don't know how you say that. Whether you're a frequentist or a Bayesian, I don't know how you begin to make a claim like. Does that just mean? Well, let's say it this way. I think one of the things your book reminds me of is that a lot of these theories have a religious nature. There's a certain holding on to belief that even though the empirical evidence hasn't come forward, that it will someday, and people want to believe that these theories are true the way religious people do. And I happen to be religious. I'm nothing against religion. It's just not the same as science. It seems like a mistake to confuse the two.
Yes, that's a very interesting remark. The issue is, though, that the people who work on this are not aware that those are beliefs. They tend to think there are good scientific reasons for why this should be true. And now the problem is that if you poke them a little bit, they have no way to justify it. I would say, of course. But the issue is they never really think about, what is it really that allows you to say that something exists, an issue like this, or what do we even mean by an explanation? What is the theory? All that kind of stuff. And so this is why my book is called Lost in Math, because they believe that just because they can write down some mathematics for it, it has to be true.
It's just a strange idea. It happens a lot in economics. We'll talk about that. And people, of course, fall in love with their theories. It's a human impulse. But I have to say that I have a number of friends who are physicists. When I told them that I was interviewing you, their first question was, "Why is that on EconTalk?" And the answer to that is because it's interesting, but it's also related to economics in a way that's not maybe obvious at first, but I hope will be by the end of our conversation. But when I asked them about your claim that these theories are empirical dead ends or have failed empirical confirmation, in particular, predicted particles have not shown up in collider experiments. I have to tell you, they looked at me kind of smugly, and there were two responses. One was, well, we're going to find them. It just hasn't happened yet, which you can believe that for a very long time, of course, right?
Yes. So that's, of course, what has been going on since the 1980s. They've started looking for this in the 1980s with the first searches for dark matter particles. And then, these supersymmetric particles, they were supposed to appear already at LEP. So that was the Large Electron-Positron Collider at CERN at the time, and it hasn't happened. And then it was supposed to be at Tevatron, and then it was supposed to be at the LHC, and again, that hasn't happened, and now they want to build a yet larger collider to find their stupid particles. And my problem with this is not so much that you want to keep pushing this energy frontier. My problem is that they are using techniques for theory development that obviously do not work. And everything that I've learned about science tells me that you should learn the lesson and stop using these methods. And that's what's not happening. And that really, really worries me, because it means there's something really going wrong in this field.
So they, of course, don't agree with you. Some of them are sympathetic. Your book is, as I said, it's a tour of what we know right now, or what we think we know, or what we might know. But it's also a set of conversations with leading physicists alive today and how they react to these kinds of concerns that you have. And they are not as concerned as you are overall. They are much more optimistic. And for me, as a non-physicist, it reminds me of economics, as I said, but it also reminds me of chemistry. You know, when the periodic table was first discovered, you know, there were holes in it, and people predicted that these elements would be discovered, and of course they were. And that led people to believe that, I don't think you mentioned it, but I think that moment in science and other related kind of moments in physics were things that were predicted, the Higgs boson being one example where things did show up. They just think, well, it is just a matter of time. We don't have powerful enough colliders. We'll eventually develop them. And all these things have to be true. They're holding on to that. And I get that. Because of that, the history seems to encourage that viewpoint.
No, it doesn't.
Okay, why not?
That's a very sloppy look at the history. So this is one of the points that I try to get across in the book, but I know that for someone who doesn't really actually know the math of the theories, it's hard to understand. So let's take this as example of the Higgs boson. If you have the standard model of particle physics without the Higgs boson, this theory just does not work at LHC energies. You cannot make predictions with it. You get probabilities that are larger than 1, so this is obviously mathematical nonsense. We knew that something had to happen to fix that problem. And the Higgs boson was the simplest idea that was on the market. Could have been something else, but really doesn't matter. We knew that there would have to be something at the LHC energies. Now, you look at an idea...
LHC being the collider of the sort of...
Yes, the Large Hadron Collider.
Right now, the best way we have to explore and find these things.
Yes, and now a lot of physicists, especially theoretical physicists, thought that the Large Hadron Collider should also see something else, for example, these supersymmetric particles. And now the thing is that the prediction for those additional particles is of an entirely different type, because these particles are absolutely unnecessary. And you see, it's really a different kind of prediction. And same thing goes for the periodic table. Once you have discovered this pattern, you know, for some of the elements, then you can say, well, you know, we'll have to fill it in here and here and here. Otherwise, it just doesn't work. You know, it has to be there, basically. The same is not the case with supersymmetry or with grand unification or something like this. We can do without it. You know, the theories work just fine without it. The standard model has no problem now that the Higgs is found. And that may very well just be the end of the story. Maybe that's it.
So you're saying we're spending a lot of intellectual energy and then physical energy in building. A lot of people are demanding, we just need to build a heavier collider with more energy that would identify potentially these unseen particles so far. If we had heavier energies, higher energy, then these heavier particles would be observable. And you're saying that's just in a way, you're saying it's a vanity project.
Well, not entirely. You know, you can do other things with a larger collider. You know, I mean, if you're slamming protons into each other, at the very least, you will learn something about the structure of the proton, right? So it's not that it's entirely useless. But if you want to know something about the unification of the forces or about supersymmetry, then I would just say, well, that's not a promising thing to do, because we have no reason to think that these things actually happen in the real world. You know, they certainly happen in certain types of math worlds, so to say. And the tragedy in this is that we do have really serious problems in the foundations of physics that do require a solution, but those don't get the attention because they're really hard to work on. So people prefer to work on something that's simple.
Yeah. Yeah, I get that. I understand that. So we had a guest on this program a while back, Paul Fleiterer from Stanford, Graduate School of Business, who critiqued a model in economics that's sometimes called the as-if model. It comes from a methodological paper Milton Friedman wrote, I think, in the 50s, which is to say that, economists assume people are rational, that they act in their own self-interest. And, of course, those are complicated statements by themselves. They sound straightforward to an economist, but they're actually quite complicated. But the analogy would be that, when a truck driver, this is, I think, Friedman's, when a truck driver goes around a corner in the rain at night, the truck driver acts as if they understand the physics of friction and fluids as they decide how much to brake and how fast to go. And similarly, the claim is, a baseball player going to catch a fly ball runs to a certain space as if they know the equation of the parabola that the ball's taking or the arc of the ball. They've solved it, act as if they know the physics behind a batted baseball. And on a muggy night, they might run to a different place because they understand that the ball is going to have a different path. And what Flederer's point is, which I think is a deep insight, is that a lot of economists made the mistake of thinking that because a model predicts well, so the model being, the baseball player knows physics and therefore acts as if they know physics and therefore I predict they will catch the ball, or I will assume that the billiards player understands the end body problem when they hit a billiard shot. And of course, that's not what they're doing. It's not what a baseball player does. It's not what a truck driver does. But Flederer's point is that if you're not careful, you start to think you've not just predicted well, but you've understood. And you start to believe that your model is capturing the underlying reality as opposed to just predicts well and may just abstract from so much of the reality that it's actually a very poor descriptor, which it is in the case of the truck driver or the baseball player. And I feel like in physics there's a tension between these two ideas. So tell me if I'm right. There's a famous quote. You'll tell me who said it. It's in your book. Nature speaks in the language of mathematics. And I think the incredible success of physics in predicting and in understanding our underlying reality has gotten many physicists to believe that the reality is mathematics, when in fact that may not be the case. So how do you react to that?
First, I have to admit I don't know from whom the quote is. It sounds like something that a lot of people could have said.
Yeah, it's in your book. I forget who it is. It's somebody famous.
Yeah, probably. So this is actually a very deep question that you should consult a philosopher for. So that's the question basically. What do we even mean by an explanation?
Yeah.
And I have to admit that I'm very much an instrumentalist. So this is also why I find this idea that reality is math just, not very useful. For me, a theory is something that you use to describe nature. And it explains something if it's more useful than just collecting the data, basically. But yeah, you're right that I think a lot of physicists actually do think that reality is math. Though again, and I said something similar earlier, I don't think that they ever really consciously think about it. It's not like they, write down their philosophical background and then work with that. It's just something that they implicitly assume, and that's particularly obvious when it comes to the multiverse that we were already talking about. So you have all this math in the theory that is entirely superfluous to describe anything we actually observe. So I would say, that's just math. Okay, so I have no problem with the math being there, but I don't think that it is real. And yet, a lot of physicists think that this has to also be real, just like our universe, all the other universes also have to be real.
Does anything, you said at some point that you used the word superfluous, and you said supersymmetry is just, We don't need it once we have the Higgs boson. Is there any practical difference? I mean, for example, if there are multiverses, I don't, and if they can't communicate, which I think is part of the theory, one response would be, well, who cares? Intellectually, I'm interested in how reality works, so I wouldn't say literally who cares, but in terms of practical application, string theory, multiverses, supersymmetry, do any of these at the current time have any practical application, which is to say that if we were to build the more expensive, higher energy colliders that supersymmetry might want to test on, is there any practical justification other than just we'll understand potentially how the world works? If those particles that are unseen, if they turn out to be out there, does it matter? Do any of the quantum level particles matter to human existence other than understanding?
So the brief answer is no, they don't have practical applications, though I have to add a footnote here, which is that string theory, the way that we usually talk about it, it's about, unifying all the interactions and bring in a quantization of gravity. But there may be other applications of string theory that people have been pursuing. And these may have applications in condensed matter physics or stuff like this. So this is an entirely different story. It's not really in the foundations of physics, but there may be applications with that. When it comes to these additional particles in supersymmetry, I find it possible. I do have a lot of imagination that maybe, I don't know, in 1,000 years or 2,000 years or who knows, these may be useful for something, but definitely not in the near future. There's nothing that I can think of that you would actually do with them except for writing down their properties in a little booklet. When I say that I'm not in favor of building this larger collider, it's not that I want to say I'm not in favor of ever building it. It's just that right now it seems to me we have more important things to do. It's not the right time to, further push on this.
See, we're not going to have teleportation. We're not going to be able to... Don't laugh.
Not anytime soon.
Don't
Sorry.
laugh. That's terrible. But I assume people have talked about it as a possible practical application at some point, Never.
Well, there's this thing that they call quantum teleportation, right? It's not going to teleport you to the United States or back.
Yeah, no, it doesn't work at, what do you call it? At the bigger level, yeah. The macro level.
It's not a portal.
Yeah, exactly. It's not a portal. Before we leave this idea of beauty and the lure of beauty, I just want to read a quote from Steven Weinberg that you give us. And I'm doing this partly because I ran into a physicist at a conference the other day, and I mentioned I was going to interview you, and I said to this physicist who happened to be trained at the University of Texas, where Steven Weinberg is, I said, "What do you think of this idea that beauty is overrated?" "Oh, no," he said. And he gave me the Steven Weinberg story about horses. So I thought that was, it seems to have permeated the discipline, at least at the University of Texas. He said the following: the horse breeder, he's talking about horse breeders, the horse breeder looks at a horse and says, "That's a beautiful horse." While he or she may be expressing a purely aesthetic emotion, I think there's more to it than that. The horse breeder has seen lots of horses, and from experience with horses knows that that's the kind of horse that wins races. End of quote. And but you make the point that that's not really a very compelling story. Why?
Well, it is something to it, of course, in the sense that you gain experience from your work and you learn something about the theories that you deal with every day. And of course, you try to carry forward this knowledge to do something else. And that's all well and fine as long as you stay within the same type of theories. Now, the problem starts if what you're really looking for is an entirely new type of theory. And now the issue is if you're using your ideals of beauty or elegance that you have derived from the past theories and try to use them as guides to new theories, you may not get anywhere. So what you're doing is basically you're putting the carriage before the horse.
Shame on you, Sabine.
And so let me maybe add that I quote this a few times in my book. There's a book by a philosopher by name McAllister, which is called Beauty and Revolution in Science, and he goes through quite a number of examples, most of them in physics actually, where what Kuhn called a revolution in science actually meant that the conceptions of beauty changed. Like one of the examples, I think that's what he starts with, is this step from the mechanistic worldview, everything is made of gears and bolts, to everything is really made of fields and particles. And then there's the switch from the classical mechanics to quantum mechanics. There are things like, we had this idea of the geocentric universe where all the planets were going in circles, to the heliocentric solar system with elliptic orbits. And so in each of these cases, the conceptions of beauty have really shifted. And I think that's what we need now. So if you're holding on to these ideals of beauty from the past, you're doing exactly the wrong thing.
It's a very deep insight. It reminds me of how, I've talked about this on the program before, in opera, for a long time, the heroine died at the end of the opera. And that was satisfying to people. They didn't go like, oh, that's horrible, I'm not going to watch that. They thought, well, that was what art did. Often a lot of books, not just operas, one of the main characters dies. And then there is a period where people didn't like that. They want a happy ending. And sometimes now I'd say today we like ambiguous endings. We think ambiguity is beautiful, which is the exact opposite of a neatly tied up happy ending story. Modern art to a large extent is about ambiguity. And I think we've come to respect and admire that as beautiful. And I think the elliptical orbit's a perfect example. Like, what's not beautiful about an ellipse? An ellipse is beautiful. You start to convince yourself. It's what you're used to. It's what everyone's doing. It's what the field is showing, and all the evidence seems to confirm it. And you convince yourself that it's more beautiful. Actually, it's more beautiful than a circle. You didn't realize it. And when it was circles, they thought that was the highest level. But now they've come to a different place. And I think that's it's a very deep insight that there's you could call it a cultural bias in how we think about models of the world. The other thing I think of all the time is that when clocks were invented, and you mentioned this in passing, when clocks were invented, the universe was a clock with the gears and the bolts and so on. And now it's like a computer, which is, shouldn't that tell people that their views of reality are conditioned by their technological advances, and maybe reality is actually none of these things?
Yeah, you should think so, but that's not the case. You're certainly right that definitely our sense of beauty has a cultural bias. It also changes over time, as you point out. So these two things already tell you that it's a stupid idea to rely on your human sense of beauty to develop new theories. There are some ingredients to our perception of beauty, I think, that are probably hardwired. In particular, this idea that symmetry,
we like symmetry,
is beautiful. Yeah, so this is not my area, but I read that it may be that we find symmetry beautiful because healthy organisms tend to have more symmetry. So that makes sense from an evolutionary perspective. But also in that case, there's no reason to think that this would tell us something about the fundamental laws of nature, about the properties of elementary particles and stuff like that.
You say something very deep, I thought, which I apologize for using the word deep. to my listeners. I'm overusing it this episode, but I can't help it. These are deep questions. You say, our brains didn't develop to serve science. They developed to serve us. And what served us well during evolution does not always serve us well in science. Elaborate on that.
Yes, that's that's kind of the key message that I was trying to get across with the book. You know, that we have all these cultural biases and social biases and cognitive biases that affect what research we find interesting, and so also affect what we work on, what research we fund. But this doesn't necessarily have a good correlation with what is promising research, in the sense of that it has the potential to correctly describe nature. And that's a big, big problem. That is basically unaddressed the way that we organize scientific research right now.
The idea that scientists would suffer from groupthink is just so appalling, I think, to a scientist, that it's very hard to look in the mirror and say that, right? I'm a big fan of the Feynman quote. The first principle is not to fool yourself, and you are the easiest person to fool. And the idea that scientists have to remember that seems ludicrous. And I think certainly in the public's eye, scientists are sitting in white lab coats, you know, looking for truth. The idea that they have tenure worries or ego involved, or they care what their friends think of them, is just, we don't like that idea. We have a very idealized picture of a scientist.
Yes, actually, I found that it's mostly scientists themselves who have a very idealized picture of scientists. I've also learned that groupthink is a really impolite word to use. The polite word is social reinforcement. But it's the same thing, of course. So the easiest way to find out that social reinforcement is a problem in a community is that people in the community deny that something like this can possibly affect them.
Right. Of course not.
And
other
that's
people.
what yes, it's only other people. It's not us. and so it's really sad. You know, you can't even talk with them about it because they're like, oh no, this would never affect us. You know, we're so rational people, blah, 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 blah.
Right. I have a very high IQ, so I don't have to worry about this. Yeah. Exactly.
I mean, they will not say this literally, but that's basically what they're thinking.
I'm talking with Sabine Hossenfelder. Her book is Lost in Math, and I want to thank Plantronics for providing the headset she's using, which is the Blackwire 5220. Sabine, you and I have something in common, which is it's an interesting role, and I love the role, and I find it somewhat disturbing. And I'm going to challenge you to reflect on the role that we play in a psychological sense. I'm going to put you on the couch. And I'm on the couch on the other side of the room, which is that we both have been going around saying that the emperor has no clothes, that there are aspects of our discipline that are either overrated or misunderstood. And when you play that role, in economics, I'm typically arguing that our empirical findings are not reliable, they're not credible, they're not replicable, they're based typically on observational studies that don't hold up. And so I go around saying that economics is a cross between epidemiology and history, which economists don't like that. They find that insulting, and they laugh and mock me often when I make the claim. And I feel like a kinship with you because I think you're doing something similar. You're telling people who, many of whom are more successful in your field as they are in mine, you're telling them that what they're doing, they're deluding themselves to some extent. How does that feel? Do you think about that? Well, you know, it does sound very similar to what I'm doing. The reason I'm doing this is that I really, really think it's necessary. This community needs some criticism because they're stuck with what they're doing, and they need to understand
what's the problem to get out of this? So I kind of feel like someone has to do it, and who will do it if not me?
But you don't have a Nobel Prize. Many of them do, right? That you're easily dismissed, as I am. And maybe I should be easily dismissed. I worry about it all the time. Maybe I'm just enjoying the fact that I like to think about how I'm not biased, or I don't have, I like to preach humility on the program. Maybe I'm so unhumble about my humility. I've got the same problem, actually. So do you worry about those things? Do you feel like when you're talking to, I sensed it in your book, when you're talking to Steven Weinberg and he's after half an hour, he feels like he's talked enough to you and you should get out. It's kind of hard to stand your ground.
Yeah, of course, they're trying to dismiss me. I know this. They will probably succeed with their attempt to ignore me. It's a little hard because, what I said in the book was basically that the LHC wouldn't see any of these particles, which at least so far turns out to be correct. Now, the particle physicists have a problem. In trying to get funding for their new collider, which makes it harder to ignore me. But yeah, you know how it goes. Public attention will move on. People will be talking about something else. That's very foreseeable. And there is a big risk that this community will just continue the same way that they have strung along for the last 40 years or something. But then at least I can say, look, I told you that this wouldn't work.
Yeah, you took a bit of a risk in writing your book. It took a couple years. You knew there was a chance that somewhere in that time period, something might come up that would make your book obsolete.
Oh my God. You wouldn't believe how many sleepless nights I've spent over this. Especially when they had this anomaly, which is in the book. I was like, oh my God, what do I do if that's a real thing? I'll have to throw out the whole plan for the book and then what?
So you found yourself rooting, cheering, and hoping that they didn't find anything, didn't you?
Well, it's more difficult, because as someone who works in the field themselves, of course, I would like to see some new data, some evidence that there's more than what we have, because that would be super, super exciting. So it would have been pretty bad for the book, okay, but it would have been exciting to be part of this breakthrough. You see what I mean? Yeah,
sure. No, I have an economics too, right? I being a skeptic and thinking that a lot of economic empirical work is not reliable, there's a temptation for me to enjoy it when there's Schadenfreude. Is that the correct pronunciation, by the way?
Yeah, it's pretty good.
How would you say it?
Schadenfreude.
Schadenfreude. So Schadenfreude. I'm going to do a better. As an American, it's very pretentious to pronounce it more accurately. So I'm going to try that. Schadenfreude. There's a certain Schadenfreude when a result gets when replications fail. There've been a bunch now in psychology. There's been a bunch in medicine. A lot of findings in observational trials do not hold up in randomized control trials. So I have to confess, I kind of enjoy that. But at the same time, like you, I'd like to know more about the world. So it'd be great if we could find out some things that are reliable. Like if coffee really is good for you or bad for you, I'd like to know. But there are plenty of studies on both sides, which makes me think we don't know at all, rather than thinking, oh, these are the good ones and those are the bad ones. And I think that's always the temptation in economics. The ones that confirm my ideology are the good ones. The ones that are challenging to it are obviously the ones that are flawed. And I've come to believe most of them are just flawed overall. And it does lead to some psychological challenges. When you said the anomaly that showed up, which anomaly are you referring to?
Oh, this is what went down in history as the Die Photon Anomaly. So there were too many decays into a channel that consists of two photons. And at the time, I think this was late 2015, early 2016, a lot of physicists thought that this might be, the long sought for evidence for whatever new particle. And there were a lot of papers written about this, which were very well cited. There were people who wrote papers that were cited 500-600 times in a matter of months. So that's pretty ridiculous. And yeah, so that's the story. It's actually, I think that's a big disease in the field. It has a name. It's called ambulance chasing. I don't know if you've ever heard of it. Yeah.
No,
sorry.
No, go ahead.
It's a systemic problem in the way that we organize citations, basically. That could be fixed, I'm not the only one who thinks that that's a problem, but no one's doing anything about it.
Yeah, I wanted to ask you about the Die Photon Anomaly, actually, because you write about it in the book, and I found this so delicious. Not the failure, but although there's a little, the Schadenfreude there is some, but you say the following, talking about this, that both experiments independently saw it, they were looking at the diphoton, substantially decreases the risk that the signal is mere coincidence. Taken together, the two experiments, they arrive at a chance of 3 in 10,000 that the excess is a random fluctuation, meaning the differences that were discovered, well, gee, maybe it could have been just random, but it was a very low probability. 3 in 10,000 seems like a low number. You say that's still, this is what I love, that's still far off the standard of certainty that particle physicists require for a discovery, which is roughly 1 in 3.5 million. So in economics, it's 5%. In social science, statistical significance is 95%. And there's a debate in statistics, and there's a big debate about whether we should just make it 1% instead of 5% for statistical significance, or whether we should not use statistical significance at all. But I think it's unbelievably entertaining that in physics, it's 1 in 3.5 million, slightly more demanding standard. But then, as you point out, a lot of studies assumed it was not random, went out and published a lot of papers on it. In fact, you say the next day there were 10 papers on it. Is that right? The next day? I mean, that's
yes.
It's incredible. And of course,
those were almost certainly people who knew in advance
or just waiting.
The announcement and who had heard the rumors.
But that turned out to be a statistical anomaly, not a real thing, not a real thing to be explained.
Yes, and these things, you look at the history of particle physics, these things happen basically all the time, that things of, the reason that we have this 5 sigma limit is that it just seems to work fairly well in practice. But there's no deep reason behind this. Like it's like with the 5% that you have, and that I know a lot of other disciplines use, like psychology and so on.
Yep.
There's no deep reason for that. It's just something that seems to kind of work in practice. So I'm following this discussion about the issue with the p-value to some extent. It's difficult.
No, it's the same issue. I mean, it's the same. It's not literally the same issue, but it's the same challenge that another way to think about it, and I think this is deeply disturbing, but I think it's important to say, I think there's an immense amount of religious faith in peer review. And all of what we've been saying so far in this conversation is that, peer review is overrated. As Brian Nozick, a psychologist and a co-author wrote, peer review and true are not synonyms. And yet, when a journalist reports on something as peer-reviewed or statistically significant, that allows them to stay the ever common studies show, as if we've found truth. And it's just not so. Certainly in the social sciences or in epidemiology or in medicine, it can be true in it's probably more likely to be true in physics, but maybe not. I don't know. I think it's a big problem that the academic priesthood is again maybe doesn't have so much clothing on.
Yeah, I think you're right that these issues are very closely related. So this reproducibility crisis that we see in psychology and parts of sociology and so on is very similar to the crisis that we have in the foundations of physics, in that this problem has been known for a long time. if you, this is something that even I learned so I studied mathematics originally, and I had to take some courses on statistics. This whole story with the p-value hacking and the post-group selection, all of this,
yep.
It was no secret that this is how you can artificially increase the significance of your findings. So people in the field could very well have improved their methodology decades ago, but they didn't do it. Why? Because it would have been inconvenient. It would have made it much harder to produce papers. And it's exactly the same thing that is going on in the foundations of physics. People have fallen in love with these models of supersymmetry. Why? Because they're easy to produce, and you know how you do the calculations, and you can put out a lot of papers in a short amount of time, and that keeps the wheels turning. And so that continues to proliferate, basically, and we're still doing this.
Well, one thing you mentioned, I'm not sure you word it this way, but part of the problem is there are a lot more physicists and a lot more social scientists than there used to be. So, got to publish. It's not like Broadway. It's not like other disciplines that are winner take all. There's room for everybody. We just need more journals if we have to. We're going to get more publications. I don't think you say there are too many physicists. I think you just say there are a lot more. But you could argue there are too many, right?
Well, I would say everything is relative. Too many for what? Obviously not enough to make progress. So the thing with the reason why I say this, that there are a lot of physicists, is that it tends to lead to fractionalization of the communities. They tend to fall apart into over-specialized niches. And that's not helpful to try to solve complicated problems that usually require that you connect very different regions. So I think that's a big problem, that basically the way that we're organizing research right now, it tends to favor people who specialize on something. Yeah. And it does not leave enough room for people who try to make these connections.
You're right. Just to give people a feel for what we're talking about here, you say since 1973, there hasn't been any successful new prediction that would supersede the standard model. And that's a long time. We're heading toward 50 years of you could call it stagnation. And we've talked about on the program before with Patrick Collison about the pace of innovation. And some people have argued that we figured out all the big stuff, all the low-hanging fruit's been picked. It's one argument. So we've kind of figured out almost everything. And the fact that we haven't found these last few pieces is not so important. It's demoralizing to the people in the field, perhaps, but other people would suggest, it's just a temporary slowdown. We'll have a big breakthrough again, like we always do. What are your thoughts on that? And in particular, do you feel like physics is less exciting today than it used to be because of these issues?
How would I know? I was around in the 1970s, but I assume it must have been very exciting when they found all these new particles and so on. But I don't think that this is something that will just resolve by itself. You have probably read this book, which is called The End of Science, by John Horgan.
No. Oh, no, I haven't.
You have not.
I've interviewed John, but I don't think I've read that book.
Okay, well, he says basically that science is coming to an end, as you hear from the title of the book, in the sense that, not that there will be no more scientists or no scientific research, but that we have discovered all the big insights, roughly speaking. And he tries to blame this on there's maybe a fundamental limit to knowledge, which we have just reached, or its limit of human cognition, basically. I find this very, very implausible because we're seeing the stagnation all over the place. It's not just the foundations of physics, but it's other disciplines that he's talking about. For example, complexity research is one that he likes to go on about. So we also have this problem in certain sectors of technology. Maybe you could add quantum technologies there specifically, which is something that I've been looking into recently. And so it looks very much like it is a systemic problem. And this is what makes me think it must be something about the way that we're organizing scientific research that just allows scientists to get stuck in these non-promising research fields because they can't get out, basically, because they have to continue to produce papers. And that's easier to do on a topic where a lot of people work on already.
Well, it's true that a lot of potentially, I don't know what a lot means. It's, as you say, it's relative, but a lot of breakthroughs, meaning more than you would expect, come from people from outside the field who get a fresh look, who aren't stuck in the box, who aren't stuck in a particular way of thinking. I am not impressed by how most physicists do economics, but maybe physicists will have a breakthrough in economics because they aren't constrained by the models and ways that economists are trained at the PhD level in the United States and elsewhere. So it's possible that we are somewhat stuck, as you say. But it seems to me, tell me what you think of this. Aren't we reaching many of the limits of data collection? I mean, it's extraordinary what we're able to see of the universe in terms of measuring particles. It's an extraordinary thing how much data we've been able to accumulate, both in terms of particle physics and also astrophysics. It's if you'd said to someone 100 years ago or 200 years ago about what we know now, they would have just said that's impossible. But it does make me wonder, and this is where I think I sympathize a little bit with Horgan, that our ability to continue to add to that database in some sense is limited in so many ways. And certainly in economics, the kind of data that we want to have, we're never going to have. And I think our ability to understand, say, the macroeconomy is fundamentally constrained because of that. Drawing on Hayek's Nobel Prize address, we'll put a link up to that. Do you think that's true in physics, that maybe our ability to discover new stuff is limited by the fact that we have picked the low-hanging data fruit? And there's just not that much more we can gather about the origins of the Big Bang or what's happening at galaxies that are in black holes, say. They're real far away. They're hard to get information about.
So it's definitely becoming more difficult. But if you look at the history of physics, what has happened so far is that we have gathered new insights about the way that nature works, and that has allowed us to develop new technologies, which have led to new insights, which have led to new technologies. And that cycle seems to be broken. And it's broken not on the data collection side, because we have a lot of data. It's broken on the theory development side, where we're just missing explanations for that data. And so I think that what you say is true. It becomes more difficult to collect new data, but that doesn't explain why we're stuck, because it's not the data collection that's the problem. Now, when it comes to economics or, society in more general, I think that's a much more complicated question. How much you can even learn from the data in principle. I don't think anyone really knows, in a system that's so complex, how much can you even get out of the data in principle?
Yeah, I think it's incredibly primitive, and it's dangerous because we look where the light is. As you point out, the drunk with the keys, lost the keys, looks under the lamppost, and economists look where the data are because that's what we have. And the idea that the data aren't good enough to answer the questions you want to answer that's not acceptable. When I suggest that, people say things like, well, this is the best data we have. And I say, but it's not good for what the question is. But it's the best data. Meaning, well, what else could you do? And the answer is, well, you'd be humble about what you can understand, but people don't like that. That doesn't sell. It's an interesting idea that we'll get more that we have a lot more data. I guess my challenge to you as an economist is it's hard to understand why so many physicists are locked in these boxes or stuck in these theoretical straitjackets, because you're suggesting there's a tremendous opportunity to get out of those jackets, to get out of those boxes and look at the world in a fresh way. And usually it'd be a bunch of people working on that. It is high risk. I get that.
Yeah, well, what can I say? I think they should listen to me.
Is anyone, Sabine? What kind of reaction has your book gotten?
Well, the people who I'm paying, they're listening to me.
What do you mean?
Well, I have some postdocs, and they do what I say, basically. But other than that, money makes things possible. To be fair, I think that the senior people in the field, by which I basically mean everyone who's older than me, basically don't care what I'm saying. But the younger people do. I know this both from the emails that I get and also from people who I meet at conferences or when I give lectures or something like this, because they don't want to work on something that is unpromising and waste the time of their life, right? Yeah. And so that's certainly a big part of the audience that I've written the book for. Yeah,
Einstein didn't have tenure when he worked on relativity, right? So, and he wasn't trying to get tenure. He was just, I think he was a clerk in a patent office, which is many great thinkers have been clerks in patent offices, I think. It's interesting. It's definitely a study to be done there. I'm going to switch gears and step way outside the confines of your book. When I interviewed Alan Lightman for this program about his recent book, Searching for Stars Off an Island in Maine, he talked about the power of transcendence. And he said, for me, as both a scientist and a humanist, the transcendent experience is the most powerful evidence we have for a spiritual world. By this, I mean the immediate and vital personal experience of being connected to something larger than ourselves, to feeling some unseen order or truth in the world. End of quote. Do you have any thoughts on that? On the existence of transcendence in human consciousness and what it might portend, what it might signify, if anything?
Yeah, it's interesting you're asking this question because that's basically what my next book will be about. So I read this book, Searching for Stars on an Island in Maine. I will admit that I didn't like it. It was not so much the content of the book as the way that it was written, with these basically disconnected essays. And also he's going on a lot about the ants that he's looking at, which kind of I thought was, I don't know, it was not really my thing. But he's touching on a lot of points that I think are really important, not just from a personal perspective of a scientist, but also to understand what science can do in our societies, what it can give to people, besides just being an explanation for a certain observed phenomenon, by delivering this, transcendent experience or a connection to a deeper meaning, which is something that I think scientists don't really like to talk about, this spiritual side. The moment you start saying spirituality to a scientist, they will roll their eyes and walk away.
Right, like philosophy. I mean, you point out in the book that physicists could benefit from talking to some philosophers, and philosophers could probably benefit from hearing from some physicists. But the idea that there's something beyond the material is, you could argue that's anti-science. I think what Lightman's book is about is an attempt to grapple with that seeming reality that there appear to our consciousness, at least, things that are beyond the material, and yet as a scientist that's creepy. So it's very hard for them.
I didn't read the book as a contrast between materialism and science. It was more, trying to understand to what extent even science is based on belief, which I think he did very well.
Yeah, of course, I'm a little bit on the spiritual side, so I tended to see that, and you're interested in that belief thing, so maybe that's what you saw. It's interesting. They're probably both in there, I think. The issue about the ants is, he likes this metaphor a lot of the ant colony that under the ground that thrives. Instead of lasting 20 years, which is the average for an ant colony, it lasts 100. And it's so long-lasting that they learn language and they write books and symphonies and beautiful music. And then one day a storm comes and destroys the whole colony and all traces of it are lost. And that's his metaphor, I think, for the human experience. We come along in the last few minutes of the universe as we know it. We might last for a while, we might not, but at some point the universe will cool off and we'll just be, all life will end, and that will be the end of it. And is there a potential for meaning in a transient world, a world that does not last? I personally don't think meaning comes from persistence, as he seems to suggest it does, but I think that's the issue. You have thoughts on that?
Well, thoughts on this, I would say enjoy it while it lasts. Maybe a little bit too shallow.
There's a long history of that viewpoint. It's got a lot of mileage on it.
Well, as someone who works in knowledge discovery, for me, this process of discovering is kind of what gives existence meaning. So I don't know. I'm not particularly bothered by knowing that it will end one day.
Even if, say, all this knowledge it's going to be lost, right? And I don't have a problem with it either, but I think the argument against it, what Lightman and others might say, is that what's the point? I mean, really, what's the point? You're going to learn as much as you can. So did Kepler. So did Aristotle, right? You have to start thinking to yourself, well, it's okay because I'm part of a long process. If you're John Gray, you don't think there's any progress being made anyway. Others would say, yeah, so you're part of a long process. It's going to end. What's the glory? Where's the poetry in being part of something that doesn't last?
Well, you ask me what's the point of life. I think that's a question we're not going to settle today.
Oh, come on. You've got at least 30 seconds. Go ahead.
Well,
no, that's a fair.
I think that we are basically part of this process of knowledge discovery, where the universe is trying to make sense of itself. You're saying that in the end it will all get lost, but if you look at what we know about the fundamental laws of nature, it basically tells you that it cannot get lost. That's the whole issue with the information loss in black holes, which I just recently made a video about, by the way.
Okay, we'll put a link to it.
So the whole reason that physicists are so upset about it is that black holes are the only thing that we know that can really, really destroy information. But without, just consider that this issue is somehow resolved and they can't do it. It basically means that the information about everything that makes you cannot get lost. It has to persist forever, just quite possibly in a form that is no longer recognizable as you.
Yeah, that's some consolation. My view on it is that, at least today, it may change tomorrow, but I like what the economist Ed Leamer says. He says we're storytelling pattern-seeking animals, and we've learned, we think we know, that the universe did not have a beginning, did not have a past before this beginning, that it just started, and that it will eventually cool down and end. And that's not a satisfying narrative. And so if you believe in God, or if you believe in the transcendent, or you believe in the immaterial or the spiritual, you'd say, well, the idea that a pitiful group of hominids on a the third rock from the sun would figure out this whole thing is ludicrous. The fact that we don't see the whole story, that's somehow a dark ending of the human experience, there's more to it. And the physicists who are atheists say there doesn't have to be more to it. It's not necessary. This could be just accepted as it is. It's just the universe came into being. And I think both sides have trouble accepting the other story. It's just a narrative that doesn't work for us. And for me, I'm very comfortable with the idea that there's more to the narrative. I don't know what more is. I sometimes think I do, or I feel something about it, but I certainly don't pretend to think we're going to, quote, discover everything. That would be so bizarre, so arrogant, so unlikely. We're doing amazingly well, but to think that if the world ends in 10 billion years, or the sun supernovas, or we destroy ourselves through nuclear weapons, that somehow that takes the meaning out of life. It's more complicated than that. I don't know exactly what it is, but it's more complicated. I'm having trouble admitting that there's a mystery there that I don't fully understand.
Yeah, I don't have a big problem with that. I just think that there are things that science cannot tell us anything about.
Yeah. My guest today has been Sabine Hossenfelder. Her book is Lost in Math. Sabine, thanks for being part of EconTalk.
Thank you.
This is EconTalk, part of the Library of Economics and Liberty. For more EconTalk, go to econtalk.org, where you can also comment on today's podcast and find links and readings related to today's conversation. The sound engineer for EconTalk is Rich Goyette. I'm your host, Russ Roberts. Thanks for listening. Talk to you on Monday.